right. This is welcome to episode 6E. This is a particularly long episode. Is because there's a lot to talk about. But essentially, what we're doing here is we're going to be taking what we applied about quadratic forms, right? And what we learned about the Hessian, and then also what we learned about the relationship between the Hessian and some scalar function. And we're going to use that to basically classify critical points of arbitrary vector functions. So what we want to do is, so let's just suppose we have f of x, okay? F of x is some multivariable function, right? So f from R n to R, right? We can take a linear approximation. So we have the linear approximation of, well, z. I'm just actually going to do L equals f of a. So linear approximation principle, right? Plus the gradient of f of a at a times x minus a, right? And then here we have this thing where f of a, the gradient at a, equals the zero vector. So that's all good, but obviously this is just going to be f of a, right? That's not helpful. So we want to go one step further, okay? And so we are going to use a quadratic approximation. Okay, so how do we do a quadratic approximation? What exactly does that mean? And, well, all we do is we want to add another term. What does that term look like? That term looks just like this. X minus a is an x. Transpose h x minus a. And remember, h is the Hessian. H is the Hessian of, right? And I should probably maybe go back and just write this a little closer. The Hessian at a, right? And that's all we add. So we end up with this quadratic approximation is equal to f at a plus the gradient f of a x minus a plus 1 over 2 x minus a transpose times the Hessian at a times x minus a. This is the quadratic approximation. So if you notice, we took some arbitrary function and we wrote it in terms of its Hessian. We wrote a quadratic approximation that includes its Hessian. Since this is, and obviously if this is a critical point, this vanishes, right? It vanishes at critical points. So that's when this is equal to 0. And so here we only have 2 points, and we only need to consider this Hessian for optimization. So we kind of have some more stuff to think about, and that's when the local, I'm going to write this down here, right? We have, if we have a critical point, right? A is local min here. If the Hessian is positive, semi-definite, then A is a local min. And 2, if if the Hessian at A is negative semi-definite, then A is a local maximum. And then 3, if the Hessian is indefinite, A is a saddle point. Yeah. Hope that makes sense. And yeah, so how we can use this to solve optimization problems is, well, if we can first find the extrema, right? We can find some A such that this is equal to 0. We can find all of those. Then all we have to do is get the Hessian. And remember, the Hessian is H is equal to just the Jacobian of the gradient of F. Right? So to find the Hessian, all we do is take the gradient and we get its Jacobian. And then from there we apply that at A. So we find the Jacobian of the gradient at A, or just the Hessian at A. Right? And then we basically can we test to see whether or not we have to find its eigenvalues. We find the eigenvalues of the Hessian, and that will tell us whether or not it's positive semi-definite or negative semi-definite or indefinite, right? So we just test for this definite ability, if that makes sense. And then from there, yeah, and then that'll tell us whether you have a local minimum, local maximum, or a saddle point. For quadratic forms, it is relatively easy, but it might be a little more challenging if you're for other functions. But it's the process is relatively straightforward. So that's that. I think we have everything we need, minus one more piece of the puzzle, and that is going to be, I think, Lagrange multipliers, which I might skip, but we'll see. And then after this, we'll get into solving some actual problems and applying this to physics. I just wanted to get all the math out of the way first, so that once I started talking about physics in multiple dimensions, then we can start using this math, and then it'll all start to kind of come together and make sense. So see you in the next one.